Hello students, welcome back to next session. So here we are going to discuss the thermoelectric refrigeration. So it is also one of the unconventional refrigeration systems. This we are going to discuss in this session. So these are all the topics we have seen so far, and now we are going to start thermoelectric refrigeration. In last session we have discussed steam jet refrigeration system. It is also known as ejector refrigeration system. So introduction, if we see here, in 1821, year 1821, Seebeck, a German physicist, observed that if a closed circuit was made of two dissimilar metals, an electric current flowed, EMF produced in the circuit when the two junctions were maintained at different temperatures. So this was the Seebeck effect, and this is the base for many electrical problems. And also we can see the change in resistance, and many things have arrived from this effect. And then there are two more effects that we are going to see in this session: Peltier and Thomson effect. However, he was unable to make use of this invention. So he found it, and when two junctions are allowed to flow a current, and those two junctions are maintained at two different temperatures. So this was the concept arrived from Seebeck. But one junction is a cold junction and another junction is a hot junction. So this cold junction is the basis for this thermoelectric refrigeration system that he has not found, but he has given this idea. With this, in 1834, Jean Peltier, a French scientist, discovered a reversed phenomena of that of Seebeck effect. So here there is a heating or cooling of a junction of a pair of dissimilar substances if the direct current is passed through them. However, he was not only able to realize the utility of the same, but also failed to correlate between his invention and that of Seebeck. So he also found it, and he also found that there are two junctions, and they both are acting in opposite in temperature nature. Then in 1838, Lenz, a German scientist, clearly showed the importance of both Seebeck's and Peltier inventions by placing a drop of water on a junction of two dissimilar metals and passing a direct current through the circuit. So he is the man where he found the temperature differences. When the current flowed in one direction, the water froze, and when the current was reversed, the ice is melted. So temperature becomes higher when the current is reversed, and when the current is flowed in one direction, the water has frozen, and this led to the concept of thermoelectric refrigeration. However, the idea did not materialize into commercial products for about a century because of the unavailability of suitable materials until the year 1930s, when semiconductors were developed. So the semiconductors came into picture in the 1930. Till then, there was no significant growth or significant development to the Lenz principle. In 1851, Thomson pointed out the third effect. He related the heat absorbed or evolved in a single conductor to the temperature gradient along it and current flowing through it. This effect takes place in addition to Joule's IR square R heating. So this is Joule's effect, IR square R, and Thomson also arrived a very similar statement like Seebeck and Peltier. So thermoelectric cooling uses the Peltier effect to create a heat flux between the junctions of two different types of materials. This effect is commonly used in camping and portable coolers and for cooling electric components and small instruments. So applying a DC voltage difference across the thermoelectric module, an electric current will pass through the module and heat will be absorbed from one side and released at the opposite side. So here heat is absorbed from one side and heat is released from another side. One module phase therefore will be cooled while the opposite phase simultaneously is heated. On the other hand, maintaining a temperature difference between the two junctions of the module, a voltage difference will be generated across the module and an electrical source is delivered. So this is what happening here. So advantages and the disadvantages. No moving parts, so it is noiseless, simple and fewer parts required, can operate in any position. These units are much more flexible than conventional units, easy control, no leakage problem, compact in size, suitable for low capacity only, and very longer life. So this is the advantage, but this is also the disadvantage. And disadvantages are a low COP, coefficient of performance, more power is needed to run the system, advantageous only for units of smaller capacity, unavailability of suitable materials of high figure of merit. So applications, Peltier refrigerators widely used in several western countries, and Peltier cooling is also used in air conditioning in air conditioned rooms where large cooling capacities are required, but the temperature differences need not to be so large. Such a system has a great advantage that it can be used for heating the room in winter merely by reversing the direction of current. So thermoelectric cooling can be effectively used in the following cases: constant low temperature bath and chambers. So cooled baffles for oil diffusion pump in vacuum system. So dew point hygrometer for determining absolute humidity and photo multiplier cooler. So serum so serum coolers for prevention of blood plasma and serums. So thermoelectric effects. When direct current passes through a pair of thermocouples with the junctions maintained at different temperatures, the following five effects are observed. Seebeck effect. When two dissimilar metals or semiconductors are connected with the junctions maintained at different temperatures, a thermoelectric force, that is EMF, electromotive force, is generated. The phenomenon of generation of EMF is called Seebeck effect. So this is the first basic effect, and here two dissimilar metals are used, and these are the two dissimilar metals, and when we join these two metals at two ends, so one junction becomes cold junction and the other junction becomes hot junction, and this is the Seebeck voltage is measured across these two metals. So the small temperature differences between the two junctions of materials A and B, the open circuit voltage developed is proportional to the temperature difference and is given by delta V equal to alpha AB into delta T. So here where delta V is open circuit voltage developed and alpha AB is Seebeck coefficient, thermoelectric power for materials A and B or P and N or smaller P and N of materials A and B. Delta T is temperature difference between the junctions of materials A and B. So the absolute Seebeck effect alpha AB of material is determined with respect to a material such as lead, in which the Seebeck coefficient is negligible. So alpha AB in semiconductors varies from 0.0002 to 0.00025 volts per degree Celsius. It does not exceed 0.0005 volt per degree Celsius in metals. The Peltier effect in direct current is passed through a pair of dissimilar metals. There is a heating at one junction, cooling at the other, depending upon the material combinations. As the function between two dissimilar metals, the heat evolved or absorbed in unit time is proportional to the current I and is given by Qp equal to pi AB into I, where Qp is the heat evolved or absorbed in unit time, so that is in terms of watts, and pi AB equal to Peltier coefficient. I is the direct current in amperes. This effect is reversible in nature. So figure shows that the arrangement of Peltier effect with dissimilar metals. So this is the figure. So here one junction becomes a cold junction and other junction becomes hot junction. So this is very similar to Seebeck effect, and these are the two metals are used. And this is Peltier effect. So next coming to Thomson effect. When a current passes through a single conductor having a temperature gradient, heat transfer is given by dx by dt equal to tau dt by dx, and where dx by dq by dx is equal to Thomson heat transfer, and all tau is Thomson coefficient, and I is flow of current through the conductor. Dt by dx equal to temperature gradient along the conductor. So Thomson effect is reversible thermoelectric phenomenon. So this is the Thomson effect simple diagram. So here temperature passes through this, and delta Q is acting here across delta X. So the temperature here will become T plus dt. So here it is T. After crossing this, it becomes T plus dt. So Jimansky obtained the following two relations connecting these three coefficients alpha, pi and tau by applying the first and second laws of thermodynamics to a simple thermoelectric circuit, that is pi AB equal to alpha AB into T, tau A minus tau B equal to T into d alpha AB by dt. From the above equations, it may be noted that the Thomson coefficient has been defined for single conductor. The Seebeck and Peltier coefficients refer to a junction between two materials. So by using those two equations, Qp equal to alpha AB into It. So this equation indicates that to get the high value of cooling or heating, alpha AB should be high. So we have to maintain alpha AB in higher values, otherwise the large current would be required. Joule effect. When the electric current flows through a conductor, there is a dissipation of electrical energy. According to the Joule, it is related to Q equal to I square R, where I and R are the current and electrical resistance respectively. The Joule effect is irreversible in nature. So conduction effect. When the ends of any element are maintained at different temperatures, there is heat transfer from the hot end to the cold end and is related by Q conduction equal to U into Th minus Tc, where U is overall conductance, Th equal to temperature at hot end, and Tc is temperature at cold end. If there is only one conductor of cross sectional area A, conductivity K and length L. The overall conductivity U is given by U equal to Ka by L. L is capital L. This effect is also irreversible in nature. So, desirable properties of thermoelectric material. A thermoelectric material should possess the following properties. So, it must be excellent conductor of electricity so that ohmic losses are minimum, and it must be very poor conductor of heat because the heat must be absorbed at one end and heat should be rejected at the other end, and it must have high thermoelectric power, meaning it must have high rate of change in voltage with temperature. A good thermoelectric material should have high electrical conductivity, low thermal conductivity, and a high Seebeck coefficient. Semiconductor is the proper material for thermoelectric refrigeration since metals are good conductors of heat and insulators are poor conductors. So this is how this property should be maintained. Analysis of thermoelectric refrigeration. The following assumptions are made in analyzing the magnitude of refrigeration effect and work done. So, heat absorption and heat rejection take place only at the junctions. Thermal conductivity and electrical resistance do not change over temperature range under consideration. No energy exchange between the conductors through space separating them. Thomson coefficient is negligible. Now, cooling and heating due to the thermoelectric effect is given by Peltier effect, that is Qc equal to pi AB into Ic, Qb equal to pi AB into Ib. So, energy transfer in thermoelectric system. So, this is the diagram, and power is given to these two ends, and this is A material and this is B material, and heat evolved here is QH. This becomes a hot junction and this becomes cold junction. So, in between we have Q, and this is the equation between these two, and thick blocks of high conducting material, and this is P type semiconductor materials, and this is N type semiconductor material, and Tc, this is the cold temperature, and Qc, that is the heat absorbed, and QH, heat released, and this is how the thermoelectric effect taking place. So, here this is the IR square heat generation. So, IR square R, so I square R, and this is the cold junction, and now this is the heat, and this is heat generation picture, and this is the heat transfer. Heat transfer is taking place, and this is positive and this is negative, and this is P type and N type material. Analysis of thermoelectric refrigeration. Easy transfer in thermoelectric system. Thermoelectric refrigeration, the heat generation in the absence of other effects will lead to heat transfer from both ends equal to 1 by 2 I square R. So, heat generation, so from figure A in earlier slides. So, considering the control volume, we have for the cold junction QE equal to 1 by 2 I square R plus U TH minus TC equal to alpha AB ITC. For the hot junction, QH plus U TH minus TC equal to alpha AB ITH plus half I square R. Thus, the thermoelectric cooling is QC equal to alpha AB ITC minus 1 by 2 I square R minus U TH minus TC, and QH equal to alpha AB ITH plus 1 by 2 I square R plus UTH minus TC. Analysis continues. Now, energy input to the system from outside as per the first law of thermodynamics is given by, so here the delta Q equal to Q net plus QH plus QC, that is equal to alpha AB ITC plus half I square R, And coefficient of performance COP, the COP is defined as COP equal to QE divided by energy supplied. So this is the equation QE. Substitute this and get this equation, that is alpha AB Tc modulus of Tc minus half I square R minus UTH minus Tc divided by alpha AB TH minus Tc plus half I square R. So this is the equation, and where overall conductance U for both conductors is given by U equal to A1 Ka plus A2 Kb by L. The total resistance for both conductors is R equal to rho 1 L1 by A1 plus rho 2 L2 by A2. So where rho is the specific resistance and gamma is the conductivity, from equation we define a term called figure of merit, that is Z equal to alpha AB by UR, that is alpha AB square by UR, and mathematical analysis shows that Z is maximum when A1 by L1, so that is alpha, that is directly proportional to rho 2 Kb by rho 1 Ka, and from the relations given by above equations one can obtain the current which corresponds to maximum COP. Maximum COP is given by COP max equal to Tc by Th minus Tc root 2 root of 1 plus Zth divided by 1 plus Ztc, and where COP max is the Carnot value of our refrigeration system operating between the upper and lower temperature limits, and from equations it is evident that COP will approach 1 when Z approaches infinity, hence COP max equal to COP Carnot. So the maximum cooling is obtained from the condition dQc by dt equal to 0, which gives I OPT equal to alpha ABTC by R ZTE root of U by R. The corresponding cooling is given by QC max equal to half ZT square into TH minus TC. The optimum COP is COP optimum equal to 1 by ZTH into TC. If the heat source is removed, the COP becomes 0 trivially. So thus the maximum temperature difference is TH minus TC max equal to half ZT square. From all the above derivations, it is evident that in order to get reasonable amount of refrigeration effect on COP, Z should be as high as possible. So that is the Z value is 0.006. So this is the figure variation in COP with temperature difference. So here the variation of COP with temperature difference, that is TH minus TC with figure of merit. So this is COP and this is TH minus TC on x-axis, and this is when the TH equal to 313 Kelvin, that is 40 degree Celsius. The Z, that is the figure of merit, is directly proportional to COP, and here this is the 0.03 curve, and this is 0.01 curve, and this is 0.005, and this is 0.002, and this is 0.001 curve. So this is how the figure of merit curve can be drawn. Variation in COP and cooling capacity with currents. So here we have another curve, and where this curve shows the variation of COP and QC with current for given value of Z, that is figure of merit, and other parameters. The curve shows how COP and QC cooling capacity change with current, where Z is equal to 0.004 K, K to the power of minus 1, TH equal to 315 K, and TC equal to 277 K, and A by L is equal to 5 millimeters. So this is the parameters taken, and this is the cooling capacity on y-axis, and x-axis we have current, and this is QC curve, and this is the COP curve, and this is the QC max. So this is QC max and this is the COP max. So these are the two peaks of these two. So material properties and thermoelectric characteristics. So here these are insulators up to the electrons per centimeter cube defines the three types of metals, that is insulators, semiconductors and metals. So up to here it is known as insulators. In between these ranges we have semiconductors and then we have metals. So these are the three factors. This is K factor and this is the I by P and this is Z figure of merit and this is alpha. So for all these four curves we can define all three types of metals through electrons per centimeter cube. So electrons per volume that defines these three type of materials, or that distinguishes between these three type of materials. A schematic representation for the range of insulator, semiconductor and metals. It is seen that Z is small for both insulators and conductors, while it is maximum for semiconductors for the given electron. So materials used in thermoelectric refrigeration system. There are various combinations of thermoelectric materials used in thermoelectric refrigeration systems. Some examples are listed here. So this is a P-type material and for figure of merit, and N-type material and the figure of merit I have listed here. And remember this value, the materials and their Z values, and Z, an index used in rating thermoelectric converters, depends on the properties of thermoelectric material used. A high value of Z is obtained by using materials with large Seebeck coefficient, small thermal conductivity, small electrical resistivity, and when you see the research is being done to find more efficient thermoelectric materials, and materials like bismuth telluride and antimony telluride, lead selenide and others are commonly used materials. So key points on thermoelectric materials. So that is PBTE, that is lead telluride, is most commonly used material for thermoelectric converters containing small amounts of either bismuth N-type or sodium P-type, and efficiency of thermoelectric converters based on PBTE is 5 to 7%, and bismuth telluride Bi2 and Te3 is highly suitable for thermoelectric materials due to its mechanical stability, operating conditions and ease of fabrication. Can be combined with other materials like bismuth selenide, antimony telluride and lead selenide for enhanced performance. And research directions here, the exploring materials such as silicon germanium semiconductors and selenium compounds for high temperature thermoelectric applications. So efficiency considerations for thermoelectric materials. Here efficiency factors high Z value and ability to operate at high temperatures. Materials required for a high efficiency component thermal conductivity should be minimized to ensure better efficiency. Mobility of current carriers, electrons or holes should be high to ensure compatibility with semiconductor conditions. The device configuration, one arm should consist of a pure hole type material and the other should be an electric type semiconductor. Low impurity concentration in the low temperature zone is critical, and the material should be resistant to cracking under mechanical stress and environmental influences. So the comparison between thermoelectric refrigeration and vapor compression system. So thermoelectric refrigeration system, in this system electrons are pumped by battery, in contrast in the vapor compression system where the vapor is delivered by the compressor at a high pressure. So electrons reach the junction of dissimilar materials and their energy decreases as they transfer heat to the surroundings. This is an analogous to the cooling or condensation of compressed vapor in the VCR, that is vapor compression refrigeration system, and electrons reduced to lower potential. The reduction of electrons to lower potential represents throttling in the vapor compression, and the heat transfer. The heat imparted to electrons at a high at the cold junction, it is transferred back to the battery and mimicking the transfer of vapor from the evaporator to the compressor. And vapor compression system, the evaporator and condenser components are crucial in transferring heat through vaporization of the refrigeration cycle. So this is the comparison, and where these are the four regular components of VCR, and here battery and two semiconductors P type and N type, and this becomes cold junction and this becomes hot junction. So this is the comparison in schematic comparison. We will see a few numerical problems here. The Seebeck coefficient of material is given by alpha, and this is the 14 into 10 to the power of minus 5 plus 350 T minus T square into 10 to the power of minus 7 volts per Kelvin. So here this is the Seebeck coefficient is given in this relation, and calculate Peltier and Thomson coefficients. So here the Peltier coefficient is pi, that is equal to alpha into T, where the alpha is we know this, and this is the Seebeck coefficient into T, and Seebeck coefficient into T, and this is the Thomson coefficient, tau equal to T into d alpha by dt. So here the tau is also in terms of T. So calculation of Peltier heat absorbed and rejected. So here in this problem, we see the statement is given like this: two junctions of a thermoelectric pair are maintained at 25 degrees Celsius and minus 25 degrees Celsius. The task is to find the Peltier amount of heat absorbed and heat rejected at the junctions. The following properties of thermoelectric materials A and B are used for the pair. So alpha A is given like this, and alpha B equal to minus alpha A, so that is P type and N type, and given T1 equal to 25 degrees Celsius, that becomes 298 Kelvin, and T2 is 248 Kelvin, and I is 8 ampere, that is current flow. So Peltier heat absorbed at cold junction is equal to alpha Bi into 1 minus Tc by Tt. By substituting the values in terms of alpha A, we are getting this QE equal to 38.64 joules. So Peltier heat rejected at the heat junction. So QH equal to alpha AI into 1 minus Tc by T. QH equal to alpha A into 8 into 1 minus 248 by 298. By substituting all these values, we are getting QH, that is the Peltier heat rejected at the heat junction. So that is equal to QH, that is equal to 48.33 joules. So next problem, thermoelectric cooling system calculation problem, and here in a thermoelectric cooling system, each couple has total electric resistance of 0.003 ohms, total thermal conductance equal to 0.025 watt per Kelvin, and thermoelectric power equal to 420 into 10 to the power of minus 6 volts per Kelvin, and calculate the figure of merit, that is Z, and TH equal to 310 K and TC equal to 270 K and I equal to 20 A. Find the cooling capacity in tons of refrigeration if 100 couples are used. So this is the given data, R equal to 0.003 ohms and U equal to 0.025 watt per Kelvin, and alpha B equal to 420 into 10 to the power of minus 6 volt per Kelvin, and I equal to 20 ampere, and TH equal to 310 Kelvin, and TC equal to 270 Kelvin, and number of couples are 100, and figure of merit can be calculated using alpha B square divided by UR, and by substituting this we are getting this value. And heat absorbed at the cooling junction per couple, so using this equation, QC equation, and we are getting QC equal to 0.668 watts, and cooling capacity for 100 couples, so 0.668 into 360, 3600 divided by 1000, so that is in terms of tons, so where 1 ton equal to 14,000. So here this is how the 100 couples in terms of tonnage we are getting. So thus the cooling capacity for 1000 couples is 0.01718 ton. So example 4, thermoelectric refrigeration system with a solar battery. So given data is voltage of solar battery equal to 6 volts, thermoelectric of temperature of hot junction equal to 38 degrees Celsius, temperature of cold junction equal to 9 degrees Celsius. Properties of thermoelectric materials are given here. Alpha P equal to 0.00016 volt per Kelvin, alpha N equal to minus 0.000002 volt per Kelvin, R pair equal to 0.003 ohms, and U pair equal to 0.02 watt per Kelvin. So objective to determine the following of the cases for maximum COP, coefficient of performance, for number of the maximum cooling effect, number of thermoelectric couples, and tonnage cooling of the unit. So these are the three we have to find. So first calculate the figure of merit, and Z with the given equation, so it is coming as 0.00216 per Kelvin, and the maximum COP is also can be found out, and number of thermoelectric couples N for maximum COP, the current I for maximum COP is given by, so this is the equation in terms of I, and by substituting all the known values, I equal to 20.64 ampere. So we are getting 20.64 ampere. Now the overall voltage drop for n couples in series is given by V equal to N into alpha P TH minus TC plus IR. So we are getting this, substituting all these values, N we can get 76 couples. So this is the first step answer. And tonnage cooling of the unit, the cooling effect at the cold junction is given by, so QE equal to N alpha P I T C. So this is the equation given for QE, and now substituting all this, QE is equal to 29 watts is the another answer. So power consumed, the power consumed by the system is P equal to VI. So that is equal to 6 into 20.64. So this is 123.84 watts. So comparison of COP with the Carnot value. So we can compare this, and TC by TH minus TC root of 1 plus ZT square by 1 plus ZTC square, ZTC square, and COP by substituting all the values, we are getting COP equal to 0.2348. So next is maximum cooling. Number of thermoelectric couples for maximum cooling required are, the current for maximum cooling is given by I equal to alpha P Tc by R. We know the Tc, alpha P and R, and I comes as 31.68 ampere. Now the number of couples to be connected in series is n equal to, this is the equation, alpha P Th minus Tc plus Ir divided by 6, and the n becomes 54 couples. So the number of couples to be connected in series are 54 couples, and maximum cooling effect Qc is given by this equation, and we know all these terms, and substituting all these terms, we are getting Qc equal to 30.53 watts. So this is the answer. So power consumed, we have to find the power consumed also. The power consumed by the system equal to P equal to Vi. So 6 volts into ampere, that is I, 31.68. So this comes 190.08 watts. And comparison of COP with the Carnot value, and by substituting all these values, 0.1594 we are getting as answer. So now to conclude this, the COP of refrigeration system decreases to 0.1594 from 0.2348 when the refrigeration is increased to 0.00785 tonnage. So when we increase the refrigeration, and COP is coming down. So that is what we are observing here, and there ends this topic. We will see another topic, air refrigeration, in next session, students. For this you can refer the books. These are the books, and you can refer Rajput. Rajput is a very good book for this particular topic, and please refer that book. Apart from that, we have all these resources. You can refer these resources also. Thank you, students. We stop here, and we will see the next topic from unit 3 in next session. Thank you.